The semiconductor industry has always been at the heart of technological innovation, powering everything from personal computers to the internet, smartphones, and cloud computing. However, two forces are currently accelerating the demand for semiconductor innovation. Of course, one has to be artificial intelligence, and the other is 5G. Both technologies are transforming the world and pushing semiconductor manufacturers to design faster, smaller, and more efficient chips that can handle the massive data processing needs of the future. Hello, everyone. Welcome to the another episode of Analytics Insight podcast, where we talk about the ever evolving tech space. And I'm your host, Priya Dialani. Now, rapid technological progress is driving demand for more powerful, efficient, and customized chips, and wherein people are investing heavily in the research and development of the semiconductor industry. Let's welcome Navin Bishnoi, AVP, Data Center Engineering and India Country Manager, Marvell Technology, to delve into how AI and 5G are shaping the semiconductor industry's next generation of chip design, highlighting the technological, strategic, and economic implications. Hi, Naveen, how are you doing?
Hello, Priya. Good to be here. Thank you for having me.
Likewise, Naveen, it's a pleasure to have you on our podcast today. And I think when we talk about semiconductor industry, I think there's a lot to that we can discuss today in our podcast. And of course, we are going to get some great insights from your end. But before we get deeper into our conversation, let's start our discussion by letting our listeners know more about Marvel Technology. So, if you could give us a brief about the company, its specialization, it would be great.
Sure. Marvell Technology or semiconductor, as we speak about, a lot of people have started learning about semiconductor, and I think they know the other Marvel. And when they learn about Marvell Technology, they actually start calling us as the superheroes of the semiconductor. Marvell is actually a semiconductor solutions company. We are in the fabless space where we design and develop semiconductor solutions primarily for the data infrastructure area. And when we say data infrastructure area, we have these data that all of us are generating through the electronics and equipments around us. These data needs to be processed, it needs to be moved, it needs to be stored, and while we do that, it needs to be kept secured. And that's what Marvell enables to ensure that the data infrastructure has the capability or the semiconductor solutions for processing, networking, storage, and security. What this means that our products are more processor in nature, the different connectivity, whether it is interconnect or switches, the storage controllers, the security modules, and many other accelerators, primarily connected into the AI, cloud, data center, enterprise, 5G, and the storage market. There are traditionally two sets of semiconductor silicon solutions that you will see. One, what we call as the standard products. It is a merchant silicon that's available on the shelf for people to pick it up and use it. And the second one, which is big again, is called the custom silicon, because you try to optimize a particular use case with a very custom silicon made for that use case and get the best total cost of ownership or the best power performance optimization. And then we do both custom and the standard silicon from our side. And our primary customers are the hyperscalers, the big enterprise, and the big OEMs and the networking players across the world who leverage these solutions in their use case of AI, cloud, and the carrier infrastructure market.
That's wonderful, Naveen, and thank you for sharing that crisp intro about Marvel Technologies. And it's really great to understand, how the company is designing and developing innovative solutions in the semiconductor space and ensuring and bringing unique value to your clients. Let's dive a little deeper now and talk about you, Naveen. You have had an incredible expertise and experience in the semiconductor space, and you have also contributed to the advisory committee for Karnataka State Skilling Committee as well as India's Semiconductor Mission R&D Ecosystem Committee. So, can you tell us more about yourself? How has your journey been till date? And what exactly is your role at Marvel today?
Yes, I've been a VLSI person since the time I started my career. My first job was Texas Instruments, and then I worked in Freescale, which is now an XP. and I've been in this role for the last 14 years. This was primarily the IBM microelectronics business of custom silicon, which they sold to global foundries, and then Marvell went and acquired that. So that's how I ended up in Marvell 6 years back, and then being part of the growth and development that's happening in India. Speaking about my role, there are two roles that I play. One, to leverage the engineering and then build the products and solutions from India. And secondly, be the face of Marvell in the ecosystem, because there's so much happening in the semiconductor. We have not just the customers, we have vendors and partners in the ecosystem. We have the government putting up the policies and the infrastructure. We have the academia creating the talent pool as well as the next generation research. And how do we bring all them together to ensure that the semiconductor ecosystem grow? And then I participate in different capacities to ensure that one, Marvell plays a role to ensure that each one of these move forward, be a partner to that. And secondly, also some places we are the driver to ensure that we drive what will happen in the data center or the 5G and some of these markets. And then specifically, like, in India, what we do, if you look at semiconductor development, you can divide it into, let's say, three layers. One is you build the building blocks, what we call as the technology, the building IPs, the technologies, and the building blocks. The second one is then you go take these to make the chip, which is the hardware design part of it. And third one, I would say, is putting the software and taking it to the productization and then get it into a systems level for our customers. Marvell India is involved in all three of this to build the building blocks, the IP and technologies, all the building blocks, right from the technology node to the external partners to the tools and flows, and then all of those to take it to a building a chip, whether it is for processor or a networking, and then building the software, validation it, and enabling it for the customer use case. All of that happens from India across the Bangalore, Pune, and Hyderabad, and then we lead that as a global R&D center right from here, building on the talent pool that we had, the great engineering skills to put a product together, and enabling the customer success.
Absolutely, and that's really interesting, Naveen. And it's always great to see how leaders like you are deeply involved in shaping the company's direction and driving real impact within the organization. I think your role clearly bridges both strategy and innovation, which kinds of set the tone for what we'll be exploring further in this conversation. Now, in terms of the semiconductor industry, I think the chip crisis was pretty much a problem of global supply chain disruption during the pandemic. The semiconductor industry, I believe, is still recovering since then, but is on the course of earning billions in sales within touching distance of its target of $1 trillion by 2030. Interestingly, this growth is being driven by generative AI, where large cloud data centers are the major consumers of high-end generative AI chips. Enterprise edge devices or personal computers and smartphones are also starting to use lightweight versions to power their gen AI requirements. At the same time, I think there is a greater need for domain specific or specialized semiconductors in industries like automotive manufacturing, healthcare, or even industrial equipments or other applications. Now, today, semiconductors are powering everything from AI and cloud computing to even 5G networks. So, how would you describe its role as the invisible backbone of the digital economy?
Yeah, you said it right, Pia, right? Means I think 5 years back, probably most of I would say, the people around us didn't recognize or understand the or like the value of semiconductor in the overall economy. And the reason I say is that if we just take India as an example, there are two big infrastructure growth that's happening in India. One is this whole physical infrastructure, right? What we see is about the smart cities, the big airports, the smart factories, and all of those things, right? And the second is the whole digital infrastructure. In many cases, India is the leading example of how to leverage digital infrastructure right from the governance and into our day-to-day use, the consumer use, right? I think we are probably the biggest consumer or the push for the digital economy or the digital infrastructure growth. Now, underneath all of this, the whole foundation is semiconductor, because anything digital will involve a data, and hence that data needs to be what I called as the processed, moved, stored, and then kept secure. So semiconductor became the driving foundation for this. Pre-COVID, people didn't know it because Probably they just got the application, it's in their hand, and then they were awed by that application or that technology rather than the underlying semiconductor. But whether it is the post-COVID supply chain challenges, whether it is some of the geopolitical and the war situations that created a so-called as again supply chain challenges, and third, the aspirations or opportunities that people thought the semiconductor will bring in being the modern world grades economy, right, which is built on this digital infrastructure, brought semiconductor right into the center of every region, every government, and then everyone's focus. And then that's what we are saying. And this infrastructure is built on those three things that I talked about: compute, connectivity, and the storage. That's how you can very top level, you can divide it. Yes, there is sensors. Yes, there is cameras and other things, and some of the other controllers required. And I'll come to it in the parallel, some of the other domain that you talked about. But in the big infrastructure space, it is these three things. And even in these three things, imagine the use case. We said that even the AI infrastructure, the use case is very different. Somebody is generating code sitting in an office, whereas somebody is generating creative images, video, and something else, whether it is from an entertainment, social media, OTT, or something else, right? So there's a lot of different wide variety use case, and hence one fits all is not a solution. And then hence a domain aware or a very custom silicon starts coming in to start solving that particular domain needs at the best power, performance, and cost perspective, and then enable the growth that's happening. But this is not only the driving factor. Yes, we do have the driving technologies like automotive, and then actually automotive is becoming into a bigger mobility as the driving factor, and then the medical and industrial and automation and many other things. So semiconductor is driving what we call as all of this as the building foundational block so that they can make the digital layer on top of it and make the world better place, a smarter place, or an intelligent place for optimizing on cost, optimizing on energy, giving a user experience, better life, and an overall a better future for all of us. So that's where semiconductor is. And many of us who have been in semiconductor for 3 decades are very proud that we are seeing this moment in our career.
Absolutely, and I think that's such a great perspective. Eventually, I think semiconductors truly are the silent enablers behind so much of our modern innovation. And it's pretty fascinating how something so small can have such a massive impact on global technology and economies alike. Building on that thought, I think with AI in the picture, I think AI is completely dependent upon semiconductors, which again, which we discussed that they are the building blocks of processing speed and efficient energy consumption, both necessary components in processing large algorithms. While the domain of AI application expands, the application of AI in the semiconductor industry increases as well to address
Yes.
these challenges using advanced chip design and architecture. So I think the relation is more symbiotic. While AI need good semiconductors, in turn on the other side, it also opens up the potential for making semiconductors technology better. So
Yes.
we need trusted, energy efficient, and intelligent silicon. These components are essential for modern data infrastructure. So, how is Marvel contributing to this shift towards smarter and more sustainable semiconductor solutions?
Yeah, you said it right. And then so let's pick AI infrastructure as an example, right? If you go to a big data center or any of these AI infrastructure, inside those big real estate buildings, you will see these huge racks. An immediate thing that you will notice is these racks having those big machines, what we call as XPU. Some of them are called GPU, DPU, TPU, NPU, OPU, many different form factors, but these are the big processing units. And the reason we call it XPU is because of that custom nature. I said domain specific or a custom nature. So X comes to signify depending on what use case, and accordingly your process unit could be there. Marvell is a big player in the custom silicon business to work with a hyperscaler, to work with some of these enterprise data centers and other players to start with a whiteboard, understand what their specs is, what their use case is, and put an architecture to create that processing unit called XPU, which is most optimized for their workload and then the constraints that they have with respect to the power performance and any cost. And this is primarily a lot in the compute element because these computes are heavy. They are big chips. They are very costly. They're very power hungry, and they are the one which has many 100 billion transistors packed inside that, and hence need a very customized architecture, design, and manufacturing approach to ensure that you get the best out of it. Now, once you do that, all of these compute elements needs to be connected. And the connection has been, if you go and see traditionally, it's usually wires that you see it around. And we used to use the copper technology, the copper wires to connect these different, the electronics and the chips across the racks, between aisles, and then between buildings. But we are reaching to a place where the speed, the bandwidth, the latency, the power of the networking is not able to keep speed with the processing power or the processing constraints similarly. And then hence we need to ensure that there has to be a lot of focus on networking. And that's where optical technology comes in, where we move from electrons to photons. And it primarily lets us have a much better latency and much better energy per bit transfer that we talk about. So that's the second place where Marvell contributes significantly in the networking domain, both in copper and optical, to ensure that these are well connected to each other. And then comes in between is the switch, which enables you to go from a source to destination and then handles your data transfer as a switch box, which again needs a very high latency bandwidth as well as a radix requirement that we need to support to ensure that this switch can fit into a data center which has millions of these computing elements deployed. Now, you also brought in point about the energy efficient and an intelligent silicon. And then that's where when you look at these data centers, these are no more measured in square feet. These are no more measured in number of cores. These are measured in now what we call as a gigawatt capacity, right? And then because that's what probably is a capacity that a nuclear power reactor can generate, and enhanced data center will be co-located with some of these things. But that's the limit of what you can provide the power. That's probably also the limit for us to saying what can we cool down if we are generating that much of power in a specific physical real estate of the area. And then hence you need to build a lot of power efficient, energy efficient architecture working with these hyperscalers and many of these enterprise to ensure that we look at the overall energy footprint. And then it is both the peak energy footprint, which is needed when you and I do a prompt or a search or a request versus a so-called as a static or average energy footprint that will be there when something is not going on, right? And then both of that needs to be optimized to ensure that some of these can be scaled to the power that we are talking about and leveraging it for the modern day use cases. So that's what is Marvell enabling, both energy efficient, but also in all the segments of processing, networking, and the storage side of it.
Definitely, Naveen, and I think with the examples that you shared, it's really interesting and fascinating to see the overall growth in the semiconductor industry, both in terms of performance and sustainability. And when we talk about the energy efficient silicon aspect in the semiconductor industry, I think they will truly shape the next era of intelligent infrastructure, and also ensuring that we are focusing on the energy efficiency aspect as well. Speaking of innovation, I think the overall industry has seen significant advancements in recent years, particularly in customization and security. Now, one of the research indicates that 47% of downstream organizations have ranked enhanced customization and availability of more comprehensive APIs or kits and boards in the top three innovations that they look forward in the semiconductor industry. But on the other hand, 47% have also ranked enhanced security among the top three. So I think security has become more like a design priority rather than an afterthought. So, how important is it to embed cybersecurity right from the chip architecture level?
Yes, so because we are dealing with data, which is yours and mine's, and then probably the corporates and the country's data. That's what we are talking about, processing and moving around. Security is paramount, and then actually AI can threat it much more than previously, because somebody sitting in a garage or a basement with the power of AI can actually disrupt a lot of things, right? So hence security is much more important. And I will look at it at three levels of, like, how the security needs to be built in, right? One, we work in a global environment. I have my Marvell is a global company. We have 40 plus offices across the world working round the clock, and the data is moving around through the data centers, through the different, infrastructure. How do we have an environment which is a mix of tools, infrastructure, which includes network and data center and everything else, have that layer of cybersecurity built in so that our development is safe. My IP is safe with me, and then so is the customers or the other IPs. And whatever I do remains with me. And then again, there is no such threat because of a phishing or something else that impacts my development. And then hence these bigger infrastructure having a threat from the security. Once we have an environment secured, the second thing is that the chip that I make, how do I make it secure when it goes and sit into the data center or these infrastructures? And hence the security has come all the way into the hardware level. We have security architectures that starts from the ground level chip architecture, the IPs that we use, and they are embedded in the chip that every time we make. So whether it is the first time I'm bringing the chip up, I'm doing a significant validation in my lab, or I send it to the customer and it's deployed in a production field, this hardware architecture inside the chip ensures that if there's a threat on misusing this chip, it can be detected and then safeguarded against. And the third layer is in the supply chain, that even during these chip manufacturing to productization, it is going across borders, across factories, and across hands. And during that time, how do we manage the tampering that can happen and any other security threat that can happen during the supply chain part of it, and keep the integrity of this on any threats that could come in, right? Whether it is the physical threats that could happen with tampering or copying it, or some of the other digital threats that could happen from the firmware, the side channel, all of that. So these three layers of security is embedded in the environment, inside the architecture, right at the IP, building up it to the chip, and then in the supply chain, so that we can have the overall security built in as part of the complete idea to a production stage.
Great, absolutely. And when we're talking about security, I think making security or embedding that right from the chip level, I think that is really important in terms of growing and scaling in a digital ecosystem and making the entire digital ecosystem more resilient. And I think it's important the mindset shift that is required in terms of, not just patching vulnerabilities, but ensuring that we are proactively designing these chips and the entire architecture with protection and security in mind. And I think that's where that shift is important. And I think we are already have achieved that shift quite efficiently. Now, since I'm talking about, the shift, I think in the dream, where semiconductors silently power the technological fabric of daily lives, the entire industry has undergone a profound transformation, which we have already discussed in terms of relentless technological breakthroughs or a heightened awareness of sustainability imperatives and the dynamic shifts in the global landscape. So, wherein, it's important while we are prioritizing efficiency and novel applications, we are
Mhm.
charting a new course towards a more scalable growth in the industry. So,
Yes.
having said that, I think the leadership in the semiconductor industry is also evolving, where we are shifting from domain focused to more data fluent. So, how are leaders adapting to orchestrate these AI driven ecosystems?
Yeah, interestingly, you asked this because this has been the transition that we are also seeing. While what was used to be a standard product, merchant silicon, where you put some chip, thinking about this could be the multiple use cases in mind, build it, manufacture, and put it on the shelf, to saying is that go partner with a customer and ensure that we foresee what will be needed and then put that chip together as a very domain or a custom there. Now, as we do that, so if you see, it is more tops down about what the end system will look like rather than saying how many transistors can I pack more, what power reduction can I do, what speed improvements that I can give, which was more bottoms up focus that we were seeing has moved into a very top down systems driven approach. What is the system that will look like and where will the hardware and software merge? What will be the architecture like? Will it be placed on the system? And there are a lot of those decisions happen, including if you think about we are generating about megawatts and gigawatts of power, how will we cool them? And hence the cooling has become part of the architecture decision. And then that thermal planning decides what will be the architecture for the chip. So it's more top down systems perspective, combining hardware, software systems, the other mechanical part, and the end use case is what's driving what would the final silicon look like. So that's one. Second, now when I come into a lot of these implementation with the advent of AI, and you talked about saying we are creating chips for AI, but how can I leverage AI for my chips design so that I can do innovation at a fast pace? I can make decisions which is based on data. I can actually do a lot of faster analysis to make more competitive specs and implementation, and hence a much better efficiency either at the system level or for the workload and in general the life cycle of the product. So that's the second, is that how do we leverage AI and the data to make a better architecture for all of those things. And then this is primarily driven by a huge collaboration across the ecosystem. No one company, no one country, no one person can do all of those things. You partner with your vendors to ensure that you get aligned on some of these importance or the constraints, but you also partner with the other people who can bring in the, let's say, the mechanical or the cooling solutions, can bring in how to manage the voltage transition from a 220 volt to something that a chip will need, can bring in what will happen if the processing is coming from here versus the networking is coming from here, and put it in as a rack to be used. So there's a lot of collaboration that is happening, which is driving these data fluent or the AI driven architecture and ecosystem.
Definitely. And I think what you highlighted, I think the way you described the evolution, I think it truly makes the semiconductor, ensures that the entire industry is becoming more interconnected and intelligent. And when we talk about the leadership, I think currently we need leadership that goes beyond technical expertise. I think it's more about fostering collaboration across AI, data, and the overall engineering to drive real innovation. So I think in terms of artificial intelligence, when we're talking about these emerging technologies, I think the entire industry is driving a remarkable accomplishment, and whether it's increasing productiveness or smart designs. So,
Yes.
one last question for you is, as Marvel accelerates innovation across AI, cloud, and 5G, what are some of the breakthrough opportunities you foresee in the next few years?
Yes, so there has been a lot of focus on what we called as the compute architecture, and a lot of people call it accelerated computing and in different forms. And that's where you see the GPUs, the CPUs, the XPUs. There's been a lot of innovation that has happened to get us to a massive compute power for us to saying we can train an AI model which has trillions of parameters, which has billions of, let's say, Wikipedia equivalent pages fed into and be trained so that you and I can do a prompt and then get the answer we want. But what has been so called as still lagging behind is the networking part of it. The study says that we talk about this data, almost close to 50% of the time, the data is actually moving. It's being transferred. It's on that network layer rather than on the compute engine, right? And if if the data is spending 50% of the time in the transfer, and if that's the bottleneck, that needs to be solved so that we get the maximum horsepower. In a very simple word, I've told a lot of people that imagine you having a Ferrari car and driving it on the Bangalore road, right? You have the best horsepower to drive, but you're bottlenecked by the networking infrastructure that you have on the road, and then you don't get the best performance from the ride that you want to. So networking, especially the interconnects, is where a lot of innovation needs to happen. Marvell is leading a lot of photonics based, the optics integrated, bringing optics right close to the chip, and a term called co-package optics that's coming in. These are the places which enables us a much better integration with higher bandwidth and lower power consumption. So that's one area for sure where innovation needs to be accelerated. The second one I talked about is the custom, right? And then also to give another example of a custom accelerator or a custom chip is think about training versus inference. Now, training is in the AI world is when a big hyperscaler is taking all the data that's available and then giving it to this big, huge infrastructure, compute infrastructure, which is networked and connected to read that, to process that, and create these model for you and I, and then create an application, whether we call it Chat GPT or Claude or a DeepSeek and then something else. So that whole thing process is called training. That one needs a huge infrastructure, huge. I'm talking about 100,000, 500,000, probably a million compute in the future. But once that is done over weeks or months of trainings and everything that's done, what we come and talk about is inference. That's where you and I come in and we say, generate a code, write an email, create a PowerPoint, modify this image, convert this video, right? And then automate these workflows, right? And all of those things, that's where what we call it as an inference. Now, inference does not need a huge compute. It is a very different architecture where you need maybe more faster speed so that when you give a prompt, it quickly go process and give you the results very quickly, right? And hence there needs to be a lot of focus on how do we make these custom silicon, which is for training versus inference, which is for a workload, which is for e-commerce versus social media versus an enterprise application. So that's the second innovation that's happening is on the custom accelerators that we do. And third one is I will get into the chip design. That's what I do. I said today, any complex chip, if we talk about these big, massive XPUs, some of the big processor and controllers that goes on the self-driving cars, some of the big chips, switch boxes and interconnects that goes into an enterprise, they have billions and tens of billions and hundreds of billion transistors in that. Imagine a chip design engineer managing the data of billions transistors on his or her laptop to be able to visualize what the architecture is, implement it in the format, the specs that we have, be able to optimize it, and then sign off saying it's ready for manufacturing. And it's humanly not possible to visualize all of those things with the traditional tools and the methods that we have. And that's where AI solution comes in as well to help us do this much better by reading this data to generate some of the code and the architecture by default, to help us optimize some of those things, to look at the reviews and the logs to figure out that can we sign off all of these things. And hence a lot of innovation is happening to improve the chip design cycle time and ensure that we bring in the best and the most complex chips for these infrastructure needs that have. So that's the three innovation that I think is happening around, and Marvell is right in front of that.
Definitely. And I think the future of semiconductors is deeply intertwined with the progress of AI and 5G. These technologies are shaping a new era of intelligent, high performance, and interconnected devices that can drive unprecedented advancements across industries. And as chip makers continue to innovate in response to the demands of 5G and AI, we can expect semiconductors to play an increasingly important role in transforming business, communication, healthcare, and countless other sectors. Well, thank you so much, Naveen, for taking out the time and effort to be on a podcast today and helping us understand that positive AI adoption results in the semiconductor industry to drive and unlock potential growth in novel designs and various resources management, as well as industrial scalability that will work to create a better future of the industry. Thank you so much for your insights, Naveen. It was lovely chatting with you.
Thank you. Definitely, the time is now, and I'm excited to make that be a better future with the semiconductor.
Definitely. So, this is for our listeners. I hope you enjoyed today's episode on the role of AI and 5G in the semiconductor industry. Stay tuned for upcoming podcast. Meanwhile, you can view all our previous podcasts on Spotify and other leading platforms. Thank you so much.